Good morning, sir. Good morning to Dr. Chandresh Kumar Maurya, sir. Welcome to the online session on AI&ML in Mallaradi Engineering College for Women, sir. Good morning, children. Good morning to one and all. Before going to the brief profile about the Dr. Chandresh Kumar, sir, I want to give the details regarding Mallaradi Engineering College for Women. Mallaradi Engineering College for Women is an autonomous institution, UGC Government of India, established in 2008, approved by AICT New Delhi and affiliated to JNT University, Hyderabad. The college has UGC autonomous status by Government of India, accredited by NAC with A grade, programs accredited by NBA, ranked by NIRF Indian ranking 2020 and 2018, accepted by MHRD Government of India, ISO 9001 2015 certified, permanently affiliated to J&H 2F12B, recognized by UGC 4A plus, rated in top engineering colleges survey 2019 by Digital Learning Magazine, AAA plus rated by Keris 360 Magazine, ranked nationwide 95th by Outlook News Magazine, ranked 3rd in Outstanding Engineering Colleges Excellence category by CSR, top 100 national ranking by Times News Magazine, 141 national ranking by India Today Magazine, platinum rated by AICTE CII Industry Linked Institute Survey, recipient of Best Colleges of the Year 2019 from Education Matters, College of the Year 2017 award from Silicon India Education, Best Engineering Colleges in Telangana and AP award from International Education Awards, Time Cyber Media Private Limited, Education Leadership Award from Devang Mehta National Education Awards, and Engineering Educator Awards from University of Bradford, UK. We are in 6th to 25th band in Atal ranking. The college has established Robotics Center of Excellence, offering training and certifications in robotics. In this regard, we are very thankful to our college management and our dynamic and visionary principal, Dr. Y. Madhulata Madam Garu, for creating wonderful opportunities for engineering students. Today's our eminent personality guest lecture to all of us on artificial intelligence and machine learning by Dr. Chandresh Kumar Maurya, sir, is working as an assistant professor in the CS department of IIT Indore since July 2020. Before that, he worked as an assistant professor at NIT Delhi and ELTE University, Budapest, Hungary. He is also worked as a research scientist at IBM Research Bangalore from 2017 to 2019. He did his PhD at the Indian Institute of Technology, Roorkee, India in 2016. He completed his master's degree from Jawaharlal Nehru University, New Delhi in 2012 and bachelor's degree from BIET, Jhansi in 2010. He is the recipient of the Prime Minister's Fellowship for Doctoral Research awarded by the Consideration of Indian Industries and Robert Bosch, Bangalore. He won the Best Poster Paper Award at Xerox Research Center India XRCI Open 2016 and interned at Microsoft India R&D Bangalore and Research and Technology Center RTC Robert Bosch, Bangalore, India in 2014. He has published several papers in the reputed international journals and international conferences. His research interest includes natural language processing, text mining, data mining, machine learning, and deep learning. So today, fortunately, he accepted our request, even though sir is busy with their academic and research work. Sir, we are very lucky and privileged to listen your class, sir. So once again, thank you, sir, and welcome to Mallaradi Engineering College for Women online session, sir. Thank you, sir. So please take over the class, sir.
Thank you very much for the wonderful introduction, Dr. Srikant. And it's my pleasure to interact with all of you, and I hope you will enjoy the session. Okay, so let me share my screen and then
yes, sir.
We'll discuss.
Thank you, sir.
Okay. Okay. Okay, so yeah, is my screen visible?
Yes, sir, visible, sir.
Okay, great. Yeah, so the theme of this webinar is AI in machine learning. And many of you might have heard of this term, AI in machine learning, right? And many of you might be thinking, okay, how should I start? And what is actually machine learning and AI? So in this talk, I'm going to cover like the basics of machine learning, what are the different categories of machine learning, and what is AI, and how machine learning is related with AI. All right. So we are going to look at the broad overview of machine learning. After that, I'll discuss two approaches. How can, if, let's say you want to do machine learning, then how can you, do some interesting stuff. Let's say you want to do prediction based on your data, or you want to classify given some classification data. Okay. So we are going to look at those things as well as some hands-on experience, so that you feel that you are actually, if you want to deploy something, you want to do something in real world, how to do that, what it takes to do machine learning in real world. All right. Okay. So what is machine learning? So machine learning is basically, let me start with something. Open my, okay. So machine learning. What is ML? Okay. So here we have this term machine learning. M is for machine and L for learning. Okay. Let us understand the term. What is learning? And if you attach this term machine, then it's machine learning. Okay. So let's understand what is learning. So there's a widely accepted definition of learning, and it is by Tom Mitchell. Tom M. Mitchell is a professor at Carnegie Mellon University, CMU, USA, and he says that if you have a machine M, okay, and you want to make it learn something, okay, if this machine wants to learn something, then it needs to, and the question is why you want to learn something. Obviously if you want to learn something, that means you want to solve some problem. Okay, that's the basic idea. So if given a machine M and you have a problem or some task, okay, the machine wants to do some task T. So this is my machine, this is my task that I want to solve by machine M. So machine M will solve this problem, this task T. And how the machine will solve this task? It solves this task based on experience. For example, if you don't have any experience in solving a problem, you cannot solve that problem. Okay. So in order to solve this task T, the machine needs to acquire some experience. Okay. So it needs to, interact with this task and gain some experience E. And when you interact on this task, or the machine interact with this task T, and it tries to acquire experience E, because if you continuously try, it's like trial and error. You okay. So if you try to solve this task, you might succeed and you might fail. That's correct. So if you succeed, then that's good, you have done your job. If you don't succeed, then you retry again. All right. So essentially what you are doing is like gaining experience. Okay. So in this process of solving this task, you are gaining some experience, right? Then as your experience, as you solve more and more tasks, then you acquire more and more experience, and we know that the person who has more experience can do many tasks, right? So similarly, the same thing is happening here, and instead of human, we have replaced this with a machine. Okay, so we are deploying machine M to solve some task, and when this machine is solving this task, it acquires some experience. All right. Now the question is, how do I measure? How do I measure if the machine has actually acquired some experience, or it is capable, uh, it is able to solve that problem or this task? Okay. So we need a performance measure. Performance performance measure. All right. We need some performance measure P for this machine. Remember, for example, when you are taking some course, okay, at the end of the course, your evaluation is done, right? right? So to assess the knowledge of that subject, right? The same thing is done with the machine in machine learning. So if you are deploying a machine M in order to solve some task T, you have to measure the performance of this machine in solving that task with respect to some performance measure. This performance measure could be anything. So usually this is defined with respect to which domain or which problem you are trying to solve. Okay. So over this course, you will look at some performance matrices, and this is the like basic definition of what machine learning is kind of thing. Okay. Um, all right. So what is machine learning? So that is like, okay, some theoretical definition somebody gave you. In real world, when you want to do some machine learning, how to do it basically is that there are some essential component if you want to do machine learning. So what you need components, required for machine learning. Let's say you are a beginner, you want to do machine learning. Okay, then in order to apply some machine learning technique to solve some problem, what you need? Okay, you need maybe first of all, what you need is data. Okay, all these machines, they are trained. Okay, when I am saying that machine wants to solve some task T based on this experience E, okay, then this task is associated with some data. Okay, so if you want to apply some machine learning to solve some problem, you need data, and there are different kind of data coming from different domain. Okay, the data could be coming from, let's say, social media, all right, or it could come from, let's say, healthcare, patient monitoring systems, for example. It could be sensor data, all right, and there are different kinds of data. And second thing you need is a model of your machine. Okay, so if you want to use machine learning to solve some problem, okay, let's say you got some problem P. So if you have some problem which you want to solve, then you need the data in that domain. Okay, let's say you want to detect whether the next email which is coming to your inbox is a spam or not. Simple example, spam or no spam. So you want to classify each email coming to your inbox whether it is a spam or no spam. All right. So in order to solve this problem, spam or non-spam, this is our problem. And in order to solve this problem, what you need is essentially is the email data, right? Email data. So that's this part, right? Once you fix the data, so whenever somebody asks you that they want to, if somebody asks you to do machine learning or apply machine learning to solve some problem, first of all, ask them to give you the data. This is one of the crucial part. Let's say you join some industry tomorrow, and your manager asked you to do machine learning. Okay, because this is what everybody is using. Okay, so first of all, you should ask, do you have the data? If you don't have the data, and then, or if you don't have enough data, then it's very difficult to do machine learning. Very, very difficult. You will not do well. Okay. So first of all, ask whether you have sufficient data or not. Okay. So second thing is that once you fix the data, kind of data, it could be, so this is the domain where you can gather the data, and there are data types as well. Before I coming to the model, let me talk about the data. Could be the text data, or it could be image data, okay, or it could be in the video format. So these are various modalities of the data as well. Okay, and the different domains produce data in different modality. Use social media data is mostly images, text, and videos. Healthcare data mostly maybe maybe the text and images. Okay, sensor data could be of any kind, and so on. Right. So that's your data, and once you have the data, Um, then what you need is the model, which kind of machine learning model you want to try out. Okay, and which model, because there are a bunch of models which have been developed over the year. So in order to choose which model is right for you, okay, you have to identify which kind of problem you want to solve. Okay, so in this case, for example, the email data classification, spam into non-spam is classification kind of problem. Okay, because we have two categories, spam or no spam. It's a two category data. So this is a classification problem. So similarly, there are regression problem, a prediction problem, and there are many types of problem in the world. Okay, so based on the type of problem and the data, you choose which model you want to use. For example, whether you want to use SVM, support vector machine, or you want to use neural network. Okay, so there are a bunch of models as well. um, yeah, and third thing you require for applying machine learning in order to solve your problem is the performance metric. This is also very important because many of the time people don't know how to evaluate the model, how good or bad it is, right? So even essentially, or at the end, once you train your model, you want to assess how good or bad the model is. Okay, with respect to some split of the data, which I'm going to mention shortly. So these are the some component that you can keep in mind, that if you want to apply machine learning, you should first have the data and enough data, and then based on the type of problem you are to solve, you go for the model and then choose the performance metric. So I'm going to discuss these things in detail, more detail. Just wait for some time. Yeah, and I also encourage to ask questions if you have any doubt or query, so that we can make it more interactive, because that's the idea of conducting webinars. Okay, so yeah, so this is machine learning. In this slide, which is here, um, what we have is that from the left, first you want to gather the data, right? So this is the data part. Okay, so data, I mean, let's say you are working for some company and the client comes to you and gives you some data. So the data come from domain experts or the client you are working with. They give you usually the raw data, right? The raw data is a unprocessed data. It is not in a structured format. Maybe they can give you, uh, for example, the email messages which the client were, receiving from their customers about issues in using the product, some product. Okay, so this data could be something like customer complaints. Okay, now you want to analyze the data and how to do that. So this is the first step. Once you gather the data, what you do, you go and you want to pre-process it. Okay, pre-processing is very important because the raw data is unstructured. It's really ugly. There are lots of challenges of getting the raw data. So if you are, if you receive the raw data, just a second. So the raw data has lots of issues. Okay, for example, the raw data, you know, it is highly unstructured data. Unstructured data. Unstructured means there is no regular pattern that you can extract directly from the data. It might have missing data. Okay, some measurements are missing, missing data, or it can be incomplete data. Okay, there are nuances of real world incomplete data. So whenever you get data from your client, is really ugly, believe me. Okay, so that's why you want to apply uh, some pre-processing technique so that it's clean data, right? And yeah, so in order to do pre-processing of your data, there are some pre-processing tools that you can use, right? And once you clean the data, you have this structured data, all right? So there is a loop. Can you see this? There is a loop. So you clean again and again unless you have the data in a required format. So that's why this loop is there. And once you have built this structured data, now data is ready. You can use it to train a model. So there is a yeah, I didn't mention this one in the requirement for applying machine learning. So once you have this data, what you have is there is some candidate model. Okay. So this is your model that you want to train on this data. And in order to train, you need to have some learning algorithm. Okay. So actually this is a learning algorithm and the model is very tightly coupled. They are very close to each other. Okay. So depending on which model you are choosing, there is a learning algorithm. Okay. So for example, neural network who have used neural networks, so you use back propagation algorithm to train this model, right? So you feed, what you do is essentially you give this structured data, let's say some data points at a time to this model, and this model tries to improve itself over time. Okay. And once you settle down after some time, you realize that this model has converged or it has been optimized enough and its performance is let's say 80% accurate over let's say training data. Then what do? What you go and take this next step where which is the deployment phase. You go and deploy your model. That means this model is ready to be used in the real world. All right. For example, in Google email, many of you might seen that some important messages they are misclassified and they go into your spam folder. Maybe it was some interview application or letter for your application, and this um, uh, email went into your spam folder. So that's why they asked to check your spam folder if by mistake Google has classified your interview call letter and it went into spam folder. And it happens because this machine or the model which has been trained, it is not doing good job, right? That's that's bad. So you don't want to send like non spam email to spam folder. That's bad. You should not be doing that. So based on that's why Google asks you to mark whether that email is a spam or not, right? So whenever you say that okay, this is not a spam, believe me, this is not a spam, then Google improve its model that next time if it is receiving and the similar call letter, it will not classify that as a spam. Okay. So that's why you should give the feedback to such kind of messages from Google, especially related to emails. All right. And yeah, once you deploy your model, and then this model is ready to be used in a real world. For example, once Google realizes that this model is ready to be used to classify emails into spam or no spam, then they put it into action, and then you use it in your day-to-day life, right? The same goes to this machine translation model. For example, Google Translate, many of you might have used, right? So the way Google Translate works, so behind the scene there is a deep learning model, so which has been trained over lots of data point. Okay, and then after they realize that this model is ready to be used, and then they put it in, they deploy it, and they deploy it where people come and use it. So whenever you feed these sentences in Google Translate, you see, okay, if you give, let's say, English sentence, it translates into maybe Hindi or some other language. All right. So over time, they also ask the feedback, right? So that they can improve their model for incorrect, let's say, translation, right? So that's why giving feedback is also important, so that these machines can improve their classification job, or let's say translation job, and so on, right? So yeah, that's like a very generic overview of what machine learning is. All right, let's move on and let's see what are different types of machine learning. Okay, any questions so far related to what machine learning is and so on? Okay, no issue.
Type your questions in chat box, ma.
Yes,
Sir will
yeah, you can
answer.
type your questions in the chat box. Okay, moving forward, let's look at what are different types of machine learning. Okay, because having a broad overview of stuff is good so that you can decide which kind of learning you want to do. Because many of these so-called data scientists, you might have seen that if you give a problem, they will say, okay, wow, I want to use machine learning, deep learning, but without understanding the problem well. So once you get a problem, you need to identify which kind of problem you want to solve, right? This is very important. Okay, which type of machine learning you want to use will depend on the problem you have at hand. So here we have different types of machine learning for different kinds of problem or the data. Okay, so somebody wants to ask question. Yeah, go ahead. Okay, not sure if I can see the chat messages. Where are they? Okay. How to exit the chat messages, Dr. Srikant?
Sir, in your laptop bottom, sir, chart, sir, CHAT.
Okay, okay.
Yes,
There is
sir.
a more and then chat. Okay.
Yes, sir.
Okay. Okay. I see. So, okay. So everything is clear. They are saying good. Uh, okay. Yeah. Okay. Let's look at different types of machine learning depending on the kind of data that you have. We have supervised learning, and then we have another category of machine learning called unsupervised learning, and we have third category called reinforcement learning. Okay, today the hands-on that I will be giving you is kind of supervised learning, and because this is one of the most popular and widely used one, the supervised learning. But real world data is often they fall into this unsupervised and reinforcement learning. But because of this kind of data that you have, we choose whether we want to go for supervised or unsupervised or reinforcement learning. Okay, let me tell you what they are. Okay, so all right, so supervised learning. Okay, so we say uh, learning problem is a kind of supervised learning when you are giving data of this format. Let's say in the email classification, if I tell you the email one, okay, so this is the email one. So you have bunch of emails, let's say email 1, 2, 3, 4, and so on. Along with this email, if I tell you, okay, along with this email, just a second, I'll. So this is the email. This is the raw text. So how many emails I have got? Let's say 1, 2, 3, 4, 5. And along with the email, if I tell you the label for each email, whether it is a spam or not. Let's say first email is a spam, so I mark it as 1. If second email is also spam, I mark it 1. If this is third email is not spam, I'll tell you it is 0. Okay, no spam, and so on. So if you have this email data, usually we call this as the raw features. So whatever text is there in the email, let's say you have owned a lottery. Okay, so this was the text written in your email, and you are saying that this is a spam, so you mark it as 1. Similarly, other email would be that something like, let's say the email says that maybe second email is also spam kind, so it's similar to you have own a maybe $1 million prize. Third email is zero, it's not spam. So a text could something like, you are invited, you are invited for, let's say, a wedding. Okay, which is not spam. Okay, so these are the raw text, right? And from the raw text we usually extract what we call as feature. So that is the feature learning or feature engineering step. That's another step I'll talk about later. Just think of that feature is something that you have collected from the email. Okay, so based on this raw text, you have these labels, right? Whenever you have these feature on this side as well as the labels on this side. Label means I'm tagging each email whether it is spam or not. Okay, whenever you have both the feature as well as the label, we call that as a supervised learning problem. Okay, it is a supervised learning problem if along with the feature, usually we denote feature by x, a vector x, and label by y. Okay, so whenever you both have x and y, we call it as a supervised learning problem, right? Similarly, to give another example of supervised learning, you can think of, let's say, if I give an image, okay, let's say this is an image, and you want to tell whether it is a uh, cat or dog image. Okay, cat versus dog, cat or dog. So you want given a new image, you want to tell whether there is a cat or dog in that image. So if I give you bunch of images, okay, so images, images one, first image, second image, third image, and so on. Along with the image, I am also telling whether that image contains a dog or cat. If it is a cat, I will say it's one. If it is a dog, I will mark it as zero. Okay, so, and so on. So whenever you both have the features x as the label y, okay, x and y pair, we call it as a supervised learning problem. All right, simple. Then next one is unsupervised learning problem. So unsupervised learning problem is if I don't give you this thing, if I cross this one, if I don't tell you the label whether the image contains cat or dog, or in the previous example, if I don't tell you whether the particular image is spam or not, then if you are getting just the features x, right? Then that's a called unsupervised learning problem. So depending on the label, your problem can be supervised learning problem or unsupervised learning problem. Simple. Then there is a third category, which is called reinforcement learning. And this is nowadays very popular because of the way it mimics the real world. So reinforcement learning closely matches the real world. That's why it's very popular nowadays. So to give an example of what reinforcement learning is, that let's say there is a child and it's a really small toddler, okay, and it wants to walk, okay, and the way parents make the child learn is by giving them some support or some, they take the help of some surface and they try to first stand and then walk. So child is walking, taking the help of, let's say, some surface or support, and it falls down, right? And then they try again, they stand up and they try again. So here there is some kind of loop mechanism. This child is walking on the surface, and couple of steps they fall and then try again, stand up and they try. After some time, if you give them some something, maybe here in this case chocolate, so we call that as a reward. So if child likes the chocolate, then they try and walk more, few more steps, right? So that's a reward function we call in reinforcement learning. So based on this feedback, so feedback is coming in terms of um, um, this chocolate or reward thing. So whenever there is some reward mechanism or penalty So yeah, it could be a reward, it could be penalty. So if you are making a mistake, I will penalize you. If you are doing good, I will give some reward. So the reward could be positive or negative. So whenever there is a feedback coming from outside world, okay, so we write something like reinforcement learning uh, literature. If you look at, so there is an agent. So this agent actually interacts with the environment, and then environments interacts. So agent interacts with the environment, and the environment gives you the uh, reward or penalty. Okay. So yeah, so there is a agent, there is an environment, and they continuously interact with each other, and based on the agent performance, you get a reward or penalty. So the same thing if you map here in the case of child. So agent, child is the agent, or agent is the child. Okay. And the environment is like, for example, the walking, the environment where the child is walking, and the feedback is kind of the chocolate, or reward is your chocolate. Okay, so based on that reward, you are making the child to learn. So agent, which is your child, is trying to learn based on the reward that it is getting. So if you give more chocolate, the child will take few more steps, right? So that's how you make the machine learning learn in this fashion, reinforcement learning. Okay. There is one more thing. In supervised learning, we have this regression. Okay, so let me tell you that quickly. So regression is another kind of supervised learning. So what is a regression? Regression is also colloquially said, sometimes known as prediction problem, although prediction is very generic. Okay, and this is a form of supervised learning in which, remember, in the email data, we have this feature X, we have this label Y. The feature is the text, some text, bunch of text, text 1, text 2, text 3, and so on. And Y is your labels, discrete labels, 1 0 and 1 1 maybe, right? So if you see the domain of Y is discrete values, all right? They are just 1 or 0, or it could, if there are more categories, it could be classification into class 1 or class 2 or class 3 and so on, right? But in some cases, in some problem, this Y, which is your predictor, the label, so we call this as a predictor. Sometimes I use another term. Okay, so we call this as a predictor, feature or predictor variable. This is your response variable, okay. And if in the case of regression problem, y is actually continuous value. It could be, let's say, something like 1.25. Second value could be, let's say, 7, and the value could be 8, or it could be, let's say, 11.5. So whenever this response variable y, it is a continuous real value, then we say that this is a regression problem rather than a classification problem. It's a regression problem. And to give a real world example, so there is a famous example of predicting the prices of the house in a city. All right, so based on the measurement of the house. Okay, so let's say house feature and the price. All right, so house feature could be, let's say, 3 bedroom, three washroom, then dining hall, one dining hall, and so on. And the price is, let's say, 200,000. Okay, and based on the other measurement 212, the house price could be, let's say, 100K or so on. So here, if you see this label, which is your price, now these are the real values, right? So this will fall into this prediction regression problem rather than the classification problem, right? So based on this response variable y, what kind of data, what is the domain of that response is, you decide whether it is a classification problem or it's a regression problem. Okay, so this is also very important to decide. Now you should be comfortable in deciding, based on the data, whether you should go for supervised learning or unsupervised learning or reinforcement learning. Yes, or you should go for classification or regression, right? So yeah, these are the like different types of machine learning, and there are like more and more terms coming over years. So in the recent times, there is called self-supervised learning, which is nowadays very popular. Another one is the meta learning. So I suggest you can take a look. You can read more about these stuffs or wiki or maybe over some blogs in which people talk about meta learning and this self-supervised learning, right? Because they tries to make they are tries to make the model learning as close to the way a human learns. So essentially that's the end goal. Whatever machine learning we are trying to do, or whatever machine we are training, we are trying to make it as good as a human, right? So that we can avoid doing repetitive tasks. That's the idea. Okay. Any questions related to this slide? Supervised learning, unsupervised learning. Is it clear? I'm just checking if there is any question. Okay. Okay, good. All right. So I'll make a little diversion now and talk about some concrete stuff rather than, giving the entire history, because we cannot cover the entire machine learning here. So let me talk about some examples of how to do a supervised learning, and after that also how to do, let's say, in particular how to do a regression problem and then a classification problem. All right, so that you feel comfortable in doing that. Okay. Before that, let me discuss one more important, very, very important concept. So in machine learning, what we are trying to do is to train a machine, okay, to solve some problem. So whenever you want to train this machine, M or model M, sometimes we call it model. So we want to train a model on your data, okay. So this machine is interacting on this data. So maybe the arrow should be the other way. So we are feeding the data to the machine, and this machine is being trained through a learning algorithm. Okay, so there is this learning algorithm. Learning algorithm. Okay. So uh, in order to make this model learn this data, we have to usually split the data into two parts, which we call as a training data. So there's a training data and there's a testing data. Okay. And usually there is another small subset of data that we call as a validation data. Validation data. Okay. So in order to make this model learn something useful, we split this data into three parts: the training data, the test data, and the validation data, right? Usually training data comprises of 60 to 70% of the whole data. So lots of training data. Test data, maybe it could be 10 to 20%, and validation could be 10% or so on. Okay. So that's our usual split of the data. So you have got some emails, let's say 100 email, reserve 70 email for training the machine. Next, let's say 20 emails for testing it, and let's say 10 images for validation. Okay. So the how these different split of the data are used is like this. So the training data is used to fit the parameters of the model. Oh my God! Now I'm saying another term. So what is the parameter of the model? So I'll wait for some time. I'm going to tell you what that is. So think about parameter is something that you want to find out the known variables in the model. Let's say you want your simplest model that you can think of is equation of a line y equal to mx plus c. Okay. So if you want to find this line based on the data, so data is y and x. So unknowns are m and c. Okay. So unknowns are m and c. So if you can find m and c, you can determine the equation of the line. Simple. And data is x and y. So based on the training data, so whenever somebody says that they want to train the model, so that means is that finding these values of m and c. So m and c are parameter. In machine learning, we call them as parameter. In calculus, we call that as unknown variables. Okay. So whenever somebody wants to train a model, that means they are want to find the unknown variables in that model. Okay. A model could be different types depending on whether you are using, let's say, SVM or neural network or decision tree or naive Bayes. There are different kinds of model. All right. So training means finding these unknown M and C. Simple. Then we have this another split, which we called validation split or validation data. And this data is used to find usually the hyperparameters in the model. Usually these are the parameters, right? So m and c are the parameters here in this case. And if there are hyperparameters, so there are some cases where these parameters they depend on some other parameter. Okay. For example, if let's say m and c are random variables. Okay, so they are function of another parameter. So these random variables are drawn from another probability distribution p, parameterized by, let's say, alpha. Okay, so if this m and c are random variable and they depend on a probability distribution parameterized by alpha, so alpha would be a hyperparameter. So this validation data is used to find these hyperparameters alpha. In some cases, people want to try out. Actually, sometimes they call it or they use this validation data to test, to know how good the model is doing. And once you have good training performance, good performance on the validation data, you test this model, whatever model you're training. So in order to assess how good these parameters m and c are, you check uh, these parameters with respect to this test data. Okay, you test these values of the parameter on this test data. So if I give, let's say, values of x and y, so you fit these x and y values coming from the test data along with these parameters found in the previous step, the training and validation. Okay, so you have found m and c from training and validation. You settled down thinking that okay, you have achieved good training accuracy or good validation accuracy. Now you want to see the performance of those parameters in real world. So you pick some samples from the test data and substitute these values here. Y and X, your test data, and M and C coming from your training. And you check whether these, for example, the equation of this line is satisfied or not. Okay. If it is satisfied, good. You have done a wonderful job. You have trained your machine well. If it is not, then you need to gather more data maybe or retrain it because of some issues maybe. Okay, so that's the idea of how machine learning is done. All right, this is a very broad overview. We are going to look at in more concrete form how, let's say, if I want to do classification or I want to do regression, how to do it in practice. All right. This is very fundamental. This slide is very fundamental in machine learning. So whenever you want to do machine learning, you have to get the data. That is your first pick the model, choose the learning algorithm, and yeah, you split your data into this format and then train it using this learning algorithm. And yeah, so there are performance matrices. The fourth one is performance metric, as I mentioned earlier also. Whether you want to track the accuracy or precision or recall, there are lots of matrices, right? So you want to track those matrices over time during training. So that's the idea. Okay, great. Let's talk about some core things. Okay. So, so this slide will talk about and linear regression. So linear regression is a form of regression, supervised learning, as I mentioned earlier, in which the feature or response variable is a continuous variable value, right? So you have this x, you have this y. When y is some real number, then we call it as a prediction problem. Or in literature or statistics, people call it as a linear regression, and it is like one of the simplest and widely used technique. It's a very classic problem, and it was popular in a statistics community. Now it's like part of machine learning, and people are using it a lot in industry or academia to solve their problem. So let's see, if you want to do linear regression, how to do it. All right, and what is a linear regression, and many other stuff you will get familiar with along uh, this topic. All right, so yeah, so I'll talk about the introduction of linear regression, then what is, for example, objective function. So yeah, this is another term. I don't know whether you are familiar with this term. So objective function is something that we optimize. So okay. And finally, if you want to solve some real world problem using linear regression, then how to do that? Okay. So to give you an example of linear regression, let's say, suppose somebody has given you some data, and this data could be something like how many hours of study you have done, and based on your hours of study, you want to determine the grade or percentage score that you will get in the final exam. Simple. So the amount of time you had spent in study and versus the which grade you are going to get. So on x-axis in this figure, we have hours of study. Let's say 0 hour, 20 hour, 40 hours, 60, 80. And on y-axis, we have this grade percentage. All right. So, so these red dots are the actual grades obtained by, let's say, different students. And that's your data points. So we call it as a data point. Okay, so that's the input data, and we are denoting the data, the hours of study by x, and the grade or percentage by y. And usually the grade or percentage, they could be anything between 0 and 100, right? So it's a continuous thing. So it's a obviously it's a regression problem rather than a classification problem. Simple. Now, the objective is the problem is to find a model which can predict the grade of a student whom you know that, let's say, a new student comes in and that student is spending X hours in study. That is we call that an X test. So you want to assess or test if some student study X hours, what is the grade that person is going to get. Okay. And in order to do that, you have to solve this linear regression problem. So this is a linear regression problem because you want to predict the continuous response variable y. Okay. And this blue line in this figure is a scatter plot that you can do in MATLAB or maybe Python using Matplotlib. So you see that this line, so this is our model line. So once you have this model, which ideally should pass through all the data red points, right? ideally this line should pass through all these red lines, but since the red lines, these red dots, right, the data points are scattered everywhere, right? And there is no way you can draw a single line which passes through all the points, because these the points are scattered in 2 dimensions, and line is usually a 1 dimension, right? So yeah, so okay, so it's not possible to draw a line which can pass through all these data points. So there are some errors made by this line. Okay, so okay, let's see. So that's the idea. We want to draw a line which can pass through most of these points, the red dots here in this case. That's our objective. Or we want to find this model. This line, in this case, line is our model. We can also, you can ask, okay, why you are drawing a straight line? Why don't you draw maybe something like maybe a polynomial curve, right? Why didn't I draw like this curve which can pass through all the data points, right? Can anybody tell me why we are going for a straight line and now this, strange curve which can pass through all the data points? Anyone has any idea? No. Okay, somebody has mentioned to explain the regression concept. Okay, good. I see that people are interested. Linear property because, okay. Okay, regression concept. Okay, just a second. Linear property because, so somebody mentioned that because of linear property. No, no. So regression is basically, let me come to open the slide again. Yeah, so regression problem is this. We have the features that's like everywhere. You need to have features, features x, the predictor variable maybe. And the problem is called regression if your response variable y has continuous value. Okay, there is, it's not discrete, right? Can you see? So 1.25, 7, 8, 11.5. There is no discrete value. In this case, we had this integer values 1, 0, or it could be 1, 2, 3, 4, 5. So if you have, let's say, discrete value, then we call it a classification problem. If the response variable y is a continuous value, we call it a regression problem. Okay, very simple, nothing complicated. And here in this case, we are not going for this complicated polynomial curve. The reason is that to find this, remember our goal is to find this line or this polynomial curve, right? So if you're drawing a polynomial, it will have lots of parameter. So what is the equation of a polynomial? If you see, so polynomial has, if p is degree polynomial of degree n, so your polynomial looks like this: a0 xn, a1 xn minus 1, dot dot dot. We have then an x, x x1 maybe, or just an. Okay. Now, if you see in this polynomial, so maybe this pink line, which is ugly looking curve, it in order to represent this mathematically, what you need is this very complicated polynomial of higher degree, maybe cubic polynomial or maybe fourth degree polynomial, right? And if you see, what is the challenge is that the number of unknown parameters. So a0, in this case, if it is a n degree polynomial which you are trying to fit to the data, so how many parameters you are estimating? A0, A1 and An. So there are total n plus 1 parameters, right? N plus 1 parameter. That's really, so finding, let's say, so in the case of simple line, so even simple line is also polynomial, right? So simple line can be represented at a0x plus a1, right? So as line equation can be written as like this, a0x plus a1. So the number of parameter in the case of a simple line, straight line, is how many parameters we have? Only two. Yes, a0 and a1 versus in this polynomial. Can you see? So this ugly, strange polynomial has lots of parameter versus this straight line. Now, from your mathematics class, you should know that in order to find n plus 1 or n unknown, how many equations do you need? Can anyone comment how many equations we need to find n unknown variables? Oh, okay. What happened? Okay. Mhm. I don't know if, yeah, okay. So people have mentioned n plus 1. Yeah, that's correct. So if you have n unknown variables, you need n plus that many equations. Okay. So solving problem involving n plus 1 or n variables is complicated than solving a problem with two unknowns. So in order to get this line, in order to get this line is simple versus finding this pink polynomial, right? So in machine learning there is a saying that you should try the simpler model first and see if it is doing your job. If it is not, then you go for complicated model. That's the usual approach we try out. First try out simple line, then if it is not doing, then you go for higher degree polynomial. That's the idea. All right. So that's why in this case, we are fitting a simple line to this data. And when I'm saying fitting a line or model to a data, is like finding the line of best fit. Okay, so we are to find a line of best fit. So let me see if I have those. Yeah, I have actually. Okay, great. So, so our goal is to find that line, equation of that line, or finding these unknown variables m and c. So now we have this, so we got this data. The data is this hours of study and the grade or percentage. That's our data, and we want to do linear regression. Why linear regression? Because response variable is a continuous variable. Okay. Now after settling the problem and we fixed that, okay, we got a linear regression problem. Let's move to the model. So I'm following the same that which recipe which I mentioned in the beginning. First you get the data, next go to the model. So I'm moving to the model part now. So our model here is a line, and in this line we used to predict y given x. So remember, if I draw a line, so equation of line is equal to mx plus c, and if I give you that equation of line is 3x plus 5, right? And if I give you the x, if I tell you that x value is 2, okay, then you can tell me what is the value of y, right? If I tell you what is the x value, then you can calculate, you can substitute this value x here and you get the value of y. Okay, so that is called prediction. So whenever given this input x, you want to compute the response variable y, we are saying that to we are saying that as a prediction of y. Okay, simple. So yeah, in this equation 1 we have this y equal to mx plus c. All of us are familiar with this equation from our geometry class. So I already mentioned the x is called a predictor variable and y is called response variable in machine learning or statistics. Earlier it was a known variable, now we are giving it a name. Simple. So given xy pairs, so we are given many xy pairs. That's our input data. So in this case, how our data looks like, we have this x, you have your y. So let's say somebody studied 2 hours, the grade is expected grade is, let's say, 30% or 0.3. Somebody studied 10 hours, expected grade is, let's say, 5 50% or zero point 0.5. Somebody studied, let's say, studied 20 hours, expected grade is, let's say, zero point 0.8, and so on, right? So we have this data x and y. So can you see we have many x1? So this is our x1, we call this as x1, this is y1, we call this as x2, second data point, this is y2, this is third data point, x3, this is our third data point here. Okay, so this is just another way to denote our data, input data, right? So what we are getting here is x1, y1, okay, x2, y2, and so on. Okay, so that's our total data. Now we want to find this line, equation of this line based on this data. So here is a question: if I want to find a equation of a line, how many data points I need? Okay, how many data points we need to determine the equation of a line? So somebody has mentioned, let me see. How did you make M and C values? That's a good question. How did I make M and C values? Yeah, that's actually finding the equation of a line. If I already tell you what M and C values are, then problem is solved, right? You don't need to find the equation of a line. So in this case, if I already tell you in this, for example, here, so this is our model line, and this is a very one of the line. Okay, this is one of the lines, y equal to 3x plus 5. If I give you this line, you can draw this line, right? But the question is, if I give many data points of this format, how you are going to draw a line? This is very complicated issue. Okay, for example, let me. Uh, that's a that's the problem. Okay, so here let's say, okay, let's say we got these input values and this is your output values, and let's say first data point is here, second data point is here. So this is your hours of study, and this is your percentage. Okay, so when I plotted this data, so the data looks like this. Okay, something like this. Our objective is to find a line which can predict, given a new data point here, what is the grade for this student. Okay, so we want to draw a line, maybe something like this. Now there are many ways to draw a line. One line could be this one. So this is our first line. I can draw another line, something like this. Second line. I can draw another line, something like this. Third line. Can you see in this 2D plane, there are many ways to draw a line. Yes. Now the question is, which line should I choose? Which line should I choose? Which line is best? How do I find that? That's our problem of finding the right line to this data. So yeah, so finding the equation of the line is finding this unknown y equal to mx plus c, right? So if I can find m and c, we are good. We can exactly determine whether this is first line or second line or third line, right? So let's see in the slide. So what is the best possible way to find that line? So recall that in when we need to find two unknown, we need two equations at least, right? So in our case, if you want to determine a line in 2D, we have two unknowns, so we need two data points. Based on two data points, I can exactly determine my line. So this is called a simple linear regression in one variable. A variable is called also called a feature, which I have already mentioned. So many of you might have seen this equation of a line. So if you are given two data points, all right, ah, maybe I'll write this one. So yeah, so if somebody give you two data point x1 y1 x2 y2, you can solve this equation, right? And you can find m values of m and c, and we are good. But in reality, we have many data points, so we want that line to pass through all the data point which we saw here, right? We want this line to pass through most of these data point, if not all, because these points are scattered everywhere and there is no way that you can find a single line which can pass through all the data point. So what happens is that there is a error coming because this line is not passing through all the data points. So here this is the picture. So on x-axis we have our sub-study, on y-axis we have our percentage grade, and these are blue dots are your data points. And we have drawn this line. Somebody draw this line. I don't know why they want to find this line, but they want to find this line to predict this new uh, value of x. Okay, x prime maybe. So when given this training data, when you are to draw this line, and this line is not passing through all the data point, what is happening is that you are getting some error. The error is this much, okay, from here to here. So why this is an error? Because your prediction for this data point, let's say this was your x1, this point is your y1, okay, and based on this x and y1 you got this point. Cool. Now your line is saying that a person or student is studying x1 hours, the grade is this much, grade is this much, this one. But in reality, the grade was this much. If you compute this y1, right, this is your y1 for this x1, right? So can you see what is happening? That line is saying that for x1 value, the prediction is this, around this one. But in reality, the grade one was this big line. So can you see the difference in the grade? So let's say this line is predicting 30%, and the actual was 50%. So if we take the difference of these two, we get this 20%, and the difference is this one. This is your 20% difference in the predictions. Right? Similarly, we call this as an error or cost of prediction. So there are two terms. So this is an error or cost of prediction. So similarly, we go look for another student. So another student was this one. So error for this one is this much, right? So this could be, this error may be 30%. This error may be just 10%. I'm just cooking up these percentages. So if you see the predictions made by this line and the actual values of these y, so there is a mismatch, right? And because of that mismatch, we are getting these errors, and that's where we try to do other stuff. Let's look at this thing, how to. Our objective is to minimize these errors so that we are very close to the actual predictions. So if a student is, let's say, getting actual percentage was 50%, and you are saying that okay, 51 51%, then you are very close to the true value, right? But if you are, let's say, making 30%, then that's really bad. Okay, so we want to be as good as this ground truth. We call that as a ground truth. So if a student was supposed to get, let's say, or the actual grade was 50%, you should be as close as to this one. So that's why we take this difference of these two, the actual one and the predicted one, and we call that as an error. Okay. um, yeah, this in this slide we form our objective function. Objective function is the something that we want to minimize. It's basically, in this case, is collect all the error and try to minimize that error. So yeah, so our predictions, we are denoting our prediction by y hat. Y is your ground truth, the actual percentage of the student, and this is what our line says the prediction is for that student. Okay, and we want to minimize this distance. We also call this distance or the error. So remember, in the earlier slide, I took the difference of these two. This is our ground truth and this is our prediction. So we take the difference in order to see how much error we are making, and over time we try to minimize that gap. So we have this difference y hat minus y, and since we have total n students or n data points, okay, so in order to estimate our parameters m and c, our goal is to find m and c based on these n students grade in our sub study. So essentially what we do is to minimize the error, and we usually in literature we square that error. Remember, in the previous case, sometimes the prediction can be up or down with respect to the ground truth. For example, if ground truth is 50 and I am saying 30, then this is my under prediction. If the ground truth is, let's say, 50 and I'm saying 70%, this is my over prediction. So can you see, if we take the difference here, we get 20%, that is positive error. And in this case, if we take the difference, we are getting negative error. Okay. And if we directly take the difference of all the errors and sum them up, they can nullify each other. So if I sum both of these errors, they will become 0%. Okay, that's bad. We should actually accumulate all the error and minimize that. Therefore, when we take the difference, we square it so that it becomes a positive number. Okay, it becomes a positive number. That's why we square it. And the summation notation tells that accumulate all the errors. And we are dividing by 1 over 2n. So essentially, this is mean or average error. So that's why we are, since we have total n data points, so we divide by n, and this 2 is coming because of this mathematical simplicity. Okay, so minima doesn't change. Minima of this function doesn't change if you remove this constant factor 1 by 2. Okay, so that's our objective function jmc. So j is cost function or error function, and it is a function of two unknown m and c. Okay, so in this second equation, what we have done is we have substituted this value of y hat with the actual equation of the line. Okay, remember, for all the data point here, okay, we are using the same equation, same line equation, in order to predict what is the value of y, right? So we substitute with y hat as with this one mxi plus c. Okay, because we are using the same line for all the data points, so that's why we can substitute y hat with this one, and that's our objective function. Now the goal is to minimize this objective function or the error function. Can anybody tell me how can we optimize? Or simple, in your geometry class or calculus class, you used to have this function, right? Y equal to s squared, and you are asked to find the minima or maxima of this function, right? What is the usual process? How do you find the minima or maxima of such functions? The parabola one? Can anybody mention something? how to optimize y equal to x square. Yeah, so somebody said that, okay, differentiate and equate to 0. That's correct. Those who remember calculus class, in order to optimize such functions, it's a parabola equation, by the way, right? You take the derivative, first derivative, and you take the second derivative, equate it to 0, right? Remember our usual, the way we optimize, right? Y equal to x square, you first do dy by dx, you equate to 0, solve that equation, then you take the second derivative and check, substitute this value into second derivative and check the sign of the second derivative. If it is positive, this is minima. If it is negative, this maxima. It could be, right. So that's how you used to do there. So the same principle you can apply here as well, and you can directly find the value of MNC by doing your calculus. So this is an exercise for you to differentiate this function with respect to first M and then C and solve for M and C. What I'm going to show you is another approach to find this minima, the values of M and C for this function. Okay. So there are two solution technique. There are actually more using matrix method and so on, which I'm not going to cover. So usual approach to solve that objective function is using calculus and using optimization. So here I think I have this values of M and C calculated. So if you solve those equations by differentiating with respect to M and C, you will get these final values of M and C, which looks like this. Okay, they look complicated, but they are not. So M is nothing but covariance of x and y and divided by the variance of x, and C is again is kind of take the cumulative value of y, subtract this term, and then divide by n. So that's your M and C. In this slide, we are going to look at another approach using optimization methods. The reason is that using calculus is not always simpler or easy to get these unknowns M and C directly, because you cannot, or it's very complicated to differentiate a complicated function. So if you remember your calculus class, if somebody asks you to differentiate sine of log of e key power some, another cos of something, then it looks very strange how to differentiate. So in real life, the objective function is very complicated. So usually we don't go for difference, the calculus way. You go for optimization way, right, which you are going to see next, to get the minima maxima values. So what is the optimization way to find the value of M and C? So what we are going to use is a known optimization technique known as a gradient descent method. So gradient descent method is an optimization algorithm. And here in this plot, let's see, uh, we have plotted this objective function g of, here we are saying that denote M and C, the parameters in our model, by W. So that objective function is a function of W. So I have actually subsumed both these parameters into a single variable W. So if you plot the graph of this cost function, it looks like a parabola. So if you look at the previous slide here, it is of this form. Equation is like y equal to x square kind of format, right? This is x square format. Okay, so it's kind of parabola. So if you plot the objective function, the graph is like parabola. Okay, this one. And the gradient descent says that if you start with some initial point W and you follow the tangent line, okay, starting with, let's say here, this is, let's say, starting W, it is a iterative procedure. So it start with some initial value of this unknown variable MNC. Okay, so you take starting value and then start move towards the minimum following these gradients. So here you draw the first gradient, and then second gradient, and then third gradient. And those who remember, at the minimum, gradient is parallel to x-axis. right? Here actually I'm saying the gradient you might not be aware of. So what I mean is basically the tangent line. Okay, so usually the gradient, uh, here it is tangent, and the gradient is a higher dimensional generalization of tangent. Okay, so in higher dimensional 3D 4D we call the tangent as a gradient kind of thing. Okay, so take my word as a, somebody raised a hand. You want to say something? I don't know if you have any question. Okay, you can type your question because I don't know if you can speak. Okay, no problem. So yeah, so basically what we are doing is that we are following the tangent, and at the minimum, if you see, the tangent has this dy by dx value equal to 0, because this is parallel to the x-axis. Okay, those who know, whenever you reach the minimum, the gradient becomes 0. The tangent is the tan theta value is 0. Okay, tan theta is 0. So the line would be parallel to x-axis, right? So this is what we do in gradient descent. We follow the tangent. We maybe I'll draw here. This is, so in gradient descent, what we are doing, let's say we start with some initial value of w here. This is your w naught. This is your objective function j of w. We are saying, okay, compute the value of this function j at this input. So we are substituting. So if I want to, if I give this equation and give you many values of x, you can find the value of y, right? So in our case, y is our j and x is our this one, this whatever is there on x-axis, right? So if I give many values of x, you can compute many values of y. The same thing we are going to do. We are saying, okay, start with some initial w, compute the y value here, and here at this point you compute the tangent. This is our tangent. Okay, the first tangent. Then where this tangent interacts with the x-axis, that's our new w1. Now it says that, okay, next take compute this value of function at this point. Okay, then draw another tangent. Maybe I'll draw with a different color so that's visible. So draw another tangent at this point here. Now this tangent might meet x-axis maybe at w2. It says, okay, compute the value of the function at this point here. Now draw another tangent, maybe which looks like here. Okay, and you get another w3. Then another compute function value another time. You get another tangent. Okay. After doing it multiple times, what happens that sometime you'll reach at this minimum point. You will hit a point which we call a w star, that is your optimal value or minimum value, and where this tangent becomes like this, and at that point it never intersect this x-axis. That's your minimum. Okay, w star is your minimum. That's the idea of gradient descent. Yeah, and there are a lot of detail you can look at. There is some, so there's actually how many steps you are taking to reach the gradient. So you think of, from practical point of view, you can think of gradient descent is like you are standing on the top of a hill and you want to move down the hill. Then how would you go towards the down the hill? Is like you look at all the sides of the mountain and see which one is like taking you very faster. So let's say there are three different types of stairs on that mountain to take you down the valley or the hill, right? So you usually go for the stairs which are really sharp. Okay, because you think that can take you down the hill very quickly. So you follow that intuition. The same intuition is used here. So I'm just skipping that because there are lots of detail. So essentially, if you continue iterating this way, you'll end up getting this W star, which is your optimal parameter, that getting M and C values, right? So here, this is a one step. shown here. Then I think guessing only one step is there. So this graph shows you the same thing which I draw earlier. So need not. Um, yeah. So in this equation two, what we are doing is this linear approximation of this function. So this is the equation of the tangent basically. So in the graph, the equation of a tangent is a line. So if you see that this is something like y equal to c plus mx kind of format. So this GAW1 is a constant, and then here m is your this one, and sorry, h is usually, yeah, set to this value. So we follow the tangent as I mentioned in that graph. So we follow the tangent. Eventually, when the tangent becomes horizontal, we reach the minimum. Okay, so yeah, so this is the equation of this. This is the most important equation in this gradient descent. So I suggest you focus on this one. So the way gradient descent does it, it finds in an iterative function different values of w's. Okay, so it finds w0 and then w1 and w2 and so on. The way I showed you earlier, right? W0, w1. So using this equation. So there's a very nice mathematical notation how to find that one. And once you iterate it many times, so alpha is called a learning rate. Basically, it says that how many, what is the step size? We call this as a step size. Step size. Okay. So when you are moving down the hill, you take some step, right? You take two stairs at a time, or you take single step. All right. So that's your step size, and this is your gradient computed at that point. And if you solve this equation or compute this value w10, w1, w2, eventually you will reach that optimal. So this is what is happening. So learning rate alpha can diverge and overshoot the minimum. So this is another caveat in the gradient descent, that if you are not following the proper step size alpha, then you can, you know, come jump and never reach the minimum, right? It takes longer time to reach the minimum. Had you taken instead this step, if you had followed this approach, this one, then you will reach the minimum in 3 steps versus this the pink one, right? So there are many ways to reach the minimum, and that's why you want to find the proper learning rate, so that you are taking less time to reach the minimum, right? That's the idea, to select the proper learning rate or the step size. Okay. People may, if you have any question, instead of raising the hand, I don't know if you can talk, you can write your question in the chat box. Okay. Anyone has any question related to this one? Yeah, actually I'm skipping or going fast little bit because I wanted to cover the entire linear regression. Okay. Yeah, suggest to write a question in the comment box so that I can read. Right. Okay, there is no new question. All right. Uh, yeah. Okay, just a second. Question is, why are we finding the minima in gradient method? Okay. The reason is that we are finding the minima because we wanted to minimize the error in gradient in the when we are fitting the line. Remember our j, what is this j? This is the cumulative error, right? J was sum of many errors, yi hat minus yi, right? This is bunch of errors that we have collected, and our goal is to, you know, minimize that error. That is why, in order to minimize that error, is basically finding the values of m and c so that this function is minimized. That's why we are finding the minima using gradient descent. All right. So in this slide, what it shows that smaller, if you choose a smaller running rate, usually the smaller is like 0.01 and so on. So if you choose these small steps, then you directly go to the minimum here. Okay. So that's why choosing this learning rate smaller lands you minimum very fast. Okay. And we are minimizing because we want to minimize our error when we are fitting the line to the data. Uh, okay. Yeah, that it completes the slide. Let me open the demo code so that you can see, and after that we'll take a break for 5 minutes and we'll see another interesting stuff. So here in this notebook we have this thing, simple linear regression code. So here I am importing some libraries from NumPy and Matplotlib. Okay, so here we run the cell, and we, in the next cell, we are importing our data. So this the data is there already, data.csv file. Maybe I'll show you the data as well. So this data is here. So this is simple data, 11 points are there. So this is our x. So there are two values. One is our, this is our feature value. This is our amount of hours that person studies, and this is the grade or percentage. Okay. So there are two values in this data file, data.csv. You can even try out on your own. So I created this simple file. All right. You can randomly generate this data or handwrite this data. So using this gen from text, we are reading this. So this is some function which reads this data from this file, data.csv, and then we are extracting the data into the numpy array. Okay, and we are doing a scatter plot of that data. So plt.scatter x and y. So plt is a short form, matplotlib is a matplot plotting library available in Python. Okay, so and then we are putting the labels. X label is hours of study, y label is test score. Then we are giving the title, that this plot has the data set as a title, and then finally we are doing this plt.show, and then we have this nice plot of our data, hours of study and then test score. All right, so we got this, plot, scatter plot, right? Then we want to fit a line. Okay, so that we can draw a line something like this, which is representative of our data. So what important thing I wanted to mention, that when we fit a line or find the equation of a line, that is basically finding the model of the data. And when we build a model of something, then we throw away all the data, we don't use the data anymore. Okay, so this is also very important of modeling, that when we fit the line or find the parameters of our model, we throw away all these blue dots and keep the uh, line equation of the line or the parameters of that line. Okay, that's our model parameter. M and C are model parameter. Now tell me, if should I keep two values, which one is simpler to keep, M and C, which are the parameter of the line, or should I keep the data? You can ask this question to yourself, which one is easier to handle, right? Obviously you should go for M and C values because you are storing just two values instead of entire data. Okay, so that's why having a model of something is basically reducing the entire data footprint and keep a representative of the data in the form of model parameters. Okay, and the good thing is that if you have the parameters, you can make predictions using that parameter for a new data point. So in the next cell, we are initializing that hyperparameters, which is your learning rate alpha. We start with some initial value, remember W naught. So we start with some initial value of C and M, and the number of iterations we are setting, okay, let's run gradient descent for 10 iterations. All right. So if you execute that cell, we are set. Then we also want to define our objective function. So here our objective function is compute sum of squared error. So essentially what we are doing is that, so point stores all the points then in that file. C and M are initial values. So the total cost, the way you computed this, you go and compute this mean squared error that we saw earlier, right? This is your ground truth or the actual percentage, and this is the predicted percentage by the equation of the line, and we are squaring it, right? And we are doing this total cost is plus equal 1. So total cost is your J of W, all right? And finally we are returning total cost divided by n, because we want to return the average error. So that's why we are dividing by n, all right? Very simple. Finally, defining the gradient descent functions. So this, there are two functions. Um, yeah, so we have this additional stuff. For example, how to compute the gradient. For example, that line in this slide, we had this um, this equation, right? This is the fundamental equation in gradient descent, Wt plus 1. How I generate the next parameter W based on the previous one and then gradient of that function. So the same thing is actually computed here. Uh, Gradient of the function with respect to all the parameters M and C. So this is what it is doing, calculating the gradient for over all the points. All right, and then how to update those parameter M and C. So what should be the next parameter W1 and C1, or sorry, M1 and C1, M2 and C2 and so on. So we are using that same, take the current value of M minus the learning rate alpha times the gradient. So we are using that equation which we saw in the slide, okay, for both M and C, because M and C are our parameters, right? And yeah, and this function, the gradient descent runner function, this function gives the C and M value as well as the cost graph. So they are like helper function to compute the cost of the objective function, okay? Because we want to check whether our function is cost or the error is minimizing or not. So for every new value of M and C, we check the cost whether it is going down or not, right? Only then we would be able to see whether this is going okay, I need to run this script, this cell, and after that we run this one. So yeah, so in this one we are calling this gradient descent runner. That means you take all the points, all the data which was there in the file. You start with some initial value of C and M and the learning rate and how many times you want to run the gradient descent. If you call that function, it returns you the final C and M, which are your optimal values, and the cost graph. Okay. So if you plot this cost graph, it looks like this. On y-axis, you have the cost and the number of iterations. So as you see on x-axis, more number of iteration, the cost or the error is going down, right? So that's the idea. If you are minimizing something, the objective function should go, the cost should go down as you iterate or take many gradient steps. That means you are going down the valley, the cost should go down, okay? And finally, if you plot, so now you find C and M, you can go ahead and plot the equation, right? Y equal to mx plus c. If I give you C and M, you can plot this equation of this line. So if I plot this equation of the line on the same plot, you can see this red line goes to very close to all the data points. That's our model. Now you can keep this red line and throw away all these blue dots. That's your data, right? That's This is like linear regression code from scratch. From scratch. I didn't use any library function, but if you want to do like linear regression in practice, you don't write code like this. There are actually libraries where you can try out. For example, this scikit library, which is popular Python machine learning library. It has already implemented this thing. So you throw away your data, it will give you the C and M value. But behind the scene, in this library, the code would be something like this only, right? So somebody must have written this code and shipped you all this code as a function, which you can directly call through your script. All right. So I'll stop here and let me know if you have any questions related to linear regression. We'll take a break for 5 minutes and then start with uh, one classification problem. Any question? Okay. I'm looking at the chat. No question? Okay. Uh-huh. Okay, then we'll take a break. Yeah, clear. Okay, so we'll take a break for 5 minutes. It's 11:56. We'll meet around 12, 12:01. All right. Then we'll look at logistic regression and sentiment analysis of Twitter data. Right. So stay tuned. Okay. Okay, I hope people are back. Uh, so this was something which I had uh, given a talk some time back while at IBM. So, so in this one we are going to talk about logistic regression and sentiment classification. And we have already seen two slides. All right. Okay, just a second. Let me minimize this one. Okay, good. Okay, so am I audible? Okay, I got some questions, I guess. Okay, okay, good. Yeah, so yeah, in this one we are going to talk about classification problem and first understand what is a classification problem, how to do it, and then we'll look at a practical example of classifying tweets or understanding the sentiment of a tweet. Okay, and we'll cost that problem as a classification problem. All right. So let's understand what is a logistic regression. Logistic regression is a, here the name is kind of contains a regression, but it's not a regression, it's a classification technique. Remember when I mentioned earlier that um, regression means something. When I mentioned regression, then I said, okay, y is y is continuous, right? Y is continuous. In classification, both are form of supervised learning. Okay, so we have this predictor response variable y. In classification, y is discrete. Okay, y is discrete means it takes the values in 0, 1, 2, or it can be minus negative also, right? It should be discrete integers probably. And when y is a real value, we call that as a regression problem, right? Here in the case of logistic regression, the name is contains the regression, but it is actually a classification method. Okay, so maybe I'll also mention some names of the models. What are the, let's say if somebody asks you what are the classification techniques. Okay, so there are many classification techniques out there. Classification techniques which you can use. So we have this simple is logistic regression, logistic regression. We have the NSVM, we have this then neural networks, and then we have the naive base, naive base, based on base rule. We have this the decision trees and so on. So there are lots of classification models. So today we are going to look at one of them, which is called logistic regression. Essentially, this is not a regression model; it is a classification model. Okay, so sometimes this is an interview question, and many people get confused whether this is used for prediction or classification. Okay, so that was a side note. So logistic regression is essentially based on classification on using the probabilities. Okay, so instead of just predicting the class label, remember in classification we predict the class, discrete class labels, whether image is cat or dog or the email is a spam or no spam. We are predicting the class. So class is the label. Okay, so instead of just predicting the class, can we give the probability score for each instance being that class? So instead of saying that image is a cat or dog image, can we say that this image contains a cat with probability, let's say 80% and the dog 0.7%, 0.3%, so that the probability sum to 1. Okay, so here that's why we call this as classification based on probability. When we assign some probability to each class. Okay, so here in this case, for each image, we are saying that the image contains a cat with probability 80%, and the dog image is a 20%. Okay, sorry, it should be 20. All right. Uh, so this is very similar to the perceptron model, those who are familiar with. So, but the perceptron, it doesn't produce probability estimates. Okay, that's the difference. Perceptron is like simplest neural network you can think of. Okay, and as I mentioned, that probability of each class should sum to 1. So it's the same probability rule, that probability should be between 0 and 1, and they should probability of positive event and the complementary event, they should sum to 1. Okay, so if probability of cat, the image being a cat image, is 0.8, then what is the probability of the image being or containing a dog is would be 1 minus the probability of cat, right? If there are only two possibilities, so you can easily find using probability complementary rules what is the probability of the image containing a dog. Simple, right? You just subtract. Okay, good. So this is we want to do. We want to do learn given an image X. So I have encoded my image or the email into this feature X, and I want to assign the label, each class label, some probability. Okay, so it tells you that this is basically conditional probability. Given an image, what is the probability that the image contains a cat? What is the probability that image contains a dog? I want to estimate that probability. Okay, so how should I do that? So logistic regression says that in order to do this probabilistic classification of your data, okay, I hope my slide is still visible, because I okay. Is my slide visible? Internet audible? Voice audible? Because I got message saying that there is issue with internet. Okay, okay, good. Okay, yeah. So logistic regression is a discriminative classification approach. In machine learning, you might hear often these two terms. One is a generative model, and another. So two kinds of model we discuss in machine learning. Model type, either it is a generative model, generative, or the model can be discriminative. Discriminative. Okay. Uh, we say a model is generative if we are estimating the joint probability x and y pairs together. So in joint probability, if given the feature x and the label y, class label y, if I'm jointly finding the probability of both these things together, then we say that model is a generative model. Okay, and again, essentially both are used for classification. So some models such as naive Bayes, it is a generative one. Okay, and the logistic regression, logistic regression is a discriminative model. So tomorrow if somebody asks you what is a generative classifier, what is a discriminative classifier, you should give this example. The naive Bayes is a generative one and logistic regression is a discriminative. Then they might ask why naive Bayes is generative model. The reason is that in generative model, the way we predict the class label y of x, so in naive Bayes, we predict the class label y given the feature x using this formula, which is popular Bayes rule, right? So yeah, okay, that's the of our favorite Bayes rule. So here, can you see The way I'm predicting the class label y is first find your joint probability p of x and y and the probability of x, your features, and take the ratios. That way you can find your class label given the feature x. So here we are modeling the joint probability. That's why this is a generative one. In the discriminative one, we directly estimate this one, p of y. We do the same thing. We want to classify, given an image or email x, we want to give the class label some probability. Okay, and in discriminative classifier, we estimate this quantity directly without modeling this one. So if you don't model this one but find this one directly, uh, then this is a discriminative one. Then you can ask this question: if I want to find this conditional probability of y, class label y given the x, how can I do that without using the Bayes rule? Okay, then you can ask this question. Okay, so this is what we are going to see, how we estimate the class label probability given the feature x in this logistic regression. So here um, here there is some notation. So we are saying that h theta x, theta is our parameter, x is our feature. It is an email or the text or the image. So x is anything, in any input, and h theta x denotes our hypothesis. H is stands for hypothesis. So h theta x is meant for this probability. What is the probability? So given the image or the email x and the parameter theta, what is that probability that that image has, let's say, if I'm denoting y equal to 1, 1 for, let's say, cat, 0 is for dog. So what is the probability that that image contains a dog or the cat? So that probability h theta x, it tells me the probability that that the image contains a cat. Okay, so again this probability can be between 0 and 1 as we discussed earlier. All right, so logistic regression model, this is important. So take a careful look this one. So as I mentioned here, in discriminative classifier, we estimate the conditional probability directly without going the Bayes rule. So here, logistic regression says that this probability of p of y equal to 1 given x and theta. Here, here is this model. H theta x is g of theta transpose x, and this g function is of this form. We call that a logistic or sigmoid function. So if you plot this function 1 over 1 plus e to power minus g, this s shape function, this is called s shape curve or function, also known as logistic or sigmoid function. Okay, so if you go towards positive infinity, the function value is very close to 1. And if you go towards minus infinity, the function value is very close to 0, which is very obvious, right? So this is your 1. So that's the property of this sigmoid function. And if you see that if I am moving towards more than 0.5, this function value is positive, right? So if yeah, so maybe I'll give you the intuition of this one so that you understand. In linear regression, let us derive logistic regression from linear regression. Okay, so linear regression, the equation was y equal to mx plus c. Okay, or in higher dimensional, this equation is sometimes written as parameter can be written in terms of many variables. I can also write theta naught plus theta 1 x. Okay, so these are just parameters, right? M and c, or theta naught and theta. So this equation both represent a line. Okay, if I write this equation into a vector format, dot product of two vectors, okay, theta 0, theta 1, and my x has two things, 1 and x1, simple feature. And if I multiply these two vectors, then we are good, right? We can based on this notation, we can move to this one. Okay, because this is dot product of two vectors. The same dot product can be written in this format: theta of transpose into x, where I am saying theta, my theta is theta naught and theta 1, and our x is nothing but 1 and x1. Okay, if I take the dot product of these two, I will get this one. Yes or no? Right? Those who know dot product, right, they can identify if they are equivalent or not. Now can you see that linear regression can be represented in this format: y equal to theta transpose x. Okay, and from this linear regression we can move toward logistic regression if we pass this theta transpose x to this sigmoid function. So this is our sigmoid function, right, which we saw earlier. So this is almost 1. These are these other values. So this is our sigmoid function. Sometimes the people mention sigmoid of z equal to 1 over 1 plus e to the power minus g. So if you plot this function, this is your function. All right. So if you go towards plus infinity, function value is almost 1. If you go towards minus infinity, function value almost 0. So in order to derive logistic regression from linear regression, so linear regression is this one: y equal to theta transpose x. If you pass this thing to this function, okay, so if I denote g equal to theta transpose x, okay, and I compute y value. So if I pass the output coming from linear regression to this sigmoid, so sigmoid of g equal to sigmoid of theta transpose x is 1 plus e to the power minus theta transpose x. Okay, that's your logistic regression model. Okay, logistic regression says that you take the dot product of your parameter and the feature vector, multiply, take the dot product of them and pass that thing, whatever you got after the dot product, through a sigmoid function. Okay, and that's your logistic regression model. So that's essentially what it is. And there is a, remember, this function gives you the probability because this function lies between 0 and 1. Can you see? This function either 0 or 1 or something in between. So that's why this function is one of the very important function in deep learning, that if you want to convert a real number into a probability, you can pass that thing to a sigmoid function. Okay, so sigmoid, this function values always between 0 and 1. So if you pass any input z, this will give something between 0 and 1. So the way you interpret that thing, the output of sigmoid is a probability because that thing is between 0 and 1. Okay, it's like squashing the input. So z can be any real number, right? So no matter which real number you are passing the sigmoid function, it will make that number to lie between 0 and 1. So you can convert your real number, may say real number was 36, to something between 0 and 1. Or the prediction was, let's say, 100 cube or 10 cube. Okay, it becomes something between 0 and 1. So everything, any real number can be squashed to something between 0 and 1, that becomes your probability. And in order to get the class label, remember, logistic regression gives you the class label. So this probability is compared with some threshold, and the threshold in logistic regression is say to 0.5, this thing which I mentioned earlier. So if you see anything above 0.5, that function is positive. Okay, and if you go below 0.5, this function is taking value in negative side. I mean, this side, it is going towards 0. Okay, not negatives. Basically, it's going towards 0. So if anything above 0.5 is going towards 1, class label 1, and it's anything below 0.5 is going towards 0, right? So that's why we compare the output, this output after squashing or passing through the sigmoid, we compare this probability to this, it is whether it is greater than 0.5 or less than 0.5. Usually, if it is greater than 0.5, we assign that class label +1, and if it is less than 0.5, we assign the class label 0. So that's how we convert the probability into a class score, class label. Okay, that's the idea. So here we are doing this thing. We are passing the dot product of theta and x to the sigmoid, and we are computing this thing, the prediction. And once we get the prediction, we compare our prediction or the probability with this threshold 0.5. That's the whole idea of logistic regression. You don't need anything else. All right. So here the interpretation of hypothesis output. So H is our, if you see in the previous slide, this is called hypothesis. S theta x is our hypothesis. All right. So what we are doing is that S theta x denotes the probability that y equal to 1, the image contains a cat or not. Okay. So the way we interpreted our hypothesis is that S theta x equal to P of y given x and theta. So here in this slide, there is another example to make your concept clear. So x here, we want to diagnose based on the tumor size, whether it is a cancer or not. Okay. So x is two feature, x naught and x1, and x naught is 1 and x1 is just tumor size. So you measure the tumor size and you want to estimate whether it is a cancer or not. So let's say once you pass that size, the feature x, to your logistic regression model, and you got this thing, s theta x equal to 0.7. What it tells you that there is a 70% chance of tumor being malignant, right? So that's how you interpret the output of logistic regression. So whatever logistic regression spits you, remember logistic regression output is always between 0 and 1. So that value essentially tells you the probability of something being positive. And here positive means malignment. Okay, so here we have this again, using probability of a positive and the complementary event. If you want to find the probability that y equal to 0, you would subtract the probability of p y equal to 1 from 1, because there are only two possibilities. So it is also called as a binary classification problem. And later at this end of this slide, we'll look at multi-class classification problem. Remember this, yeah, we have two class, so it is a binary classification. Malignment or non-malignment, spam or not spam, cat or dog, only two classes are there. So it's a binary classification. All right, so that's the interpretation. So there is another interpretation of logistic regression output. So the way, if we take this two probabilities, probability of y equal to 1 and probability of y equal to 0, take the ratio, take the log, it boils down to this one, which is nothing but your linear regression. All right. So, and whenever you take the ratio of two probabilities, probability of 1 and 0, we call that as odds. Those who have a good understanding of probability theory, we have this odds of something. Okay, so odds of y equal to 1, that's your ratio, and the log of odd is equal to your linear regression. That's another interpretation of logistic regression. So here we have mentioned this one. Logistic regression assumes that the log odd is a linear function of x. Can you see, this is a linear function of x? Why? Because we are using a single power of x. Nowhere we are having x squared. Okay, so in linear regression we use single power of x. We don't square or cube. Okay, there is no x2 x3. That's why this is a linear function. If had it was theta 0 and theta 1 x square, it's a quadratic function. Those who know, right? Okay, so log of odds in the logistic regression is equal to a linear function. That's another interpretation that I wanted to show you. All right, so let's move. Yeah, logistic regression we have already seen. S theta x is g of G is here earlier I mentioned sigma of G. In some books, people mention sigma of G. Some in books follow this sigma. G is for sigmoid function. This function looks like this. So how do we interpret the output? Logistic regression output, as I mentioned earlier. If my output from logistic regression is greater than or equal to zero 0.5, we say it is class 1. If that probability is less than 0.5, we say it's class 0. Here in this picture, we can see that if something is, confidence is very high, is you can also interpret the output of logistic regression as confidence. So if confidence is greater than 0.5, is class 1, otherwise class 0. Simple. Okay. Now you can ask, can we, instead of linear line, linear decision boundary, can we draw complicated polynomial also? Okay, so that is called non-linear decision boundary. Okay, so earlier we looked at simple decision boundary in the previous slide here. Okay, but if you want to have something like this, okay, then how to do that is, what you do is you take your original features, 1 x1 x2. Let's say you had two measurement x1 and x2. This one is usually called as bias and intercept term, and you do this feature transformation, or also known as basis function expansion, two features. So our original features are x1 and x2. These are some measurements. Let's say this was the room size, length and width. Okay, or something else, some feature, some measurement of your data, right? And basis function expansion says that you can derive many features based on one of these two features. For example, you multiply those features, you square them, you square one, multiply with the other, square the other, multiply with the first one, and so on. So this is a basis function expansion. Based on two features, you are getting many features. And based on these features, you can now multiply these features with additional coefficients, a is not, a1, a2, a3, and so on, right? And you multiply these together, you'll get a polynomial of this type, which I mentioned in the previous slide of linear regression. All right. So this is also very important in machine learning, which we call it feature engineering stuff, and then doing complicated things. Right. This is your A side. Okay, logistic regression. So how to actually learn the model parameter in logistic regression. So given these data points, we have n data points, uh, where xi is feature vector in d dimension and yi is some label into 0 or 1. Or remember, our model is s theta x is g of theta transpose x, and g is this function. And theta is a vector in d dimension, and x is another vector in d dimensions. Okay, good. That's our setup. And the objective function, the similar to what we saw in the linear regression. So objective function in the linear logistic regression is not using this squared loss, or a squared error function. Remember, in linear regression, we use this mean or average squared error, right? We use that one, those who remember. So we don't use the same loss function here. Instead, the reason is that because this function is this one. So if we substitute s theta x here, this function is a non-convex optimization problem. Okay, this function is a non-convex optimization problem, and in general, solving a non-convex optimization is hard. Okay, because there is a no uh, single minimum or maximum of such functions. So if there is single minimum, we can easily find it, right, using gradient descent. If there are many minimums, local minimum, then finding minimum of such function is not easy. The reason is that gradient descent, if you run gradient descent in this function, your gradient descent will return local minima, not the global minima, this one. Okay, So non-convex is something where there are multiple minima and maxima kind of thing. Okay, I mean, just to give an example. So we don't use squared loss, squared error function in logistic regression. Instead, we estimate the model parameter using another approach in popular machine learning. We call this maximum likelihood estimation, MLE. MLE. And if you focus, this is very, very simple. Uh, those who know Bayes rule, I don't know. So Bayes rule says that posterior, Bayes rule is this one, right? P of y given x equal to P of x given y, P of y given P of x, right? Those who know uh, detailed Bayes rule, okay? In statistical machine learning, we say this is a posterior probability, posterior, and usually we remove this term. So this term, it becomes proportional to this one. So posterior becomes proportional to, we call this term as likelihood, like KE, likelihood multiplied with, we call this term as prior. So based on the prior, that in initial belief, prior is initial belief, our model parameter, that parameter is 0.5. And likelihood, which comes from the data, we reinforce our prior based on the likelihood and get the posterior. So posterior is proportional to likelihood times the prior. Okay. So in maximum likelihood estimate, what we do is like we estimate this likelihood from the data. Okay. That's the idea of likelihood. So likelihood of the data is given by this term. So P of, so there are n data points. So we are multiplying all these uh, probabilities. Okay. And yeah, there are something missing here. So I suggest you take a read wiki page of maximum likelihood estimation. Here I'm skipping something because of lack of time. All right. So here we are taking the product of many probabilities and we want to maximize that probability kind of thing. Okay. And we want to estimate our parameter theta. So in order to do that parameter estimation, we take the argmax. Argmax tells you which parameter theta gives the maximum value of this function over here. And usually maximizing the product of many functions is not easy. We actually take the log, so product of many functions, right? Many probabilities. So usually instead of minimizing the product of many probabilities, we take the log. So log, the interesting property of log, we know that the product becomes the sum. So if I take the log of this, it becomes the sum and log goes inside. And this is what we call as uh, likelihood, log likelihood. This is known as log likelihood. This term is a likelihood and this term is, there is a log, so we call this log likelihood. And instead of maximizing, we change the sign and we put a minus sign, we minimize this term. So we say this is a likely log likelihood minimization problem. So I suggest that you read this stuff. What is the MLE, maximum likelihood estimation, and how do we minimize it? Okay, so yeah, so yeah, there are a lot of detail here. The loss function, we expand this formula for this log likelihood formula, which comes like this expanded formula. And in deep learning, we call this as a binary cross entropy. There is another name for this loss function, binary cross entropy. Okay, there is another interpretation for this one. Sometimes people say there's a log loss, log error function, or log loss. So it's another, error function, some error function. So don't get afraid with the math. It's just some loss function, some error function that we want to optimize. So finally, logistic regression objective function is this one, the negative log. There is a negative sign, so we call this NLL, negative log likelihood. Okay, negative log likelihood, because there is a negative sign, there is a log, and the whole thing is a likelihood. So that's why this is a negative log likelihood, and we want to minimize this one. And yeah, there is an intuition in this slide also. I'll share this slide after the talk, you can take a look. So there is another intuition, how what is the intuition for this objective function. I'm not going to talk about that. um, I'll show you directly the equation. So yeah, finally, so there is some regularization concept in machine learning in order to avoid the overfitting, underfitting, other stuff. So what you do, you can compute the gradient descent. So you can run the gradient descent on this objective function and you can find the minimum value of theta. Okay, that's your optimal value, and where you can find this parameter. And there are other stuff actually. Yeah, this is, yeah, they have used this gradient stiff. Usually we start with some initial value of theta and you repeat, you iteratively get many values of theta, right? Theta 0, theta 1, theta 2, and so on, and you will find the optimal theta star, right, at the end of, let's say, 100 iterations and so on. So that's your equation. Yeah, in this slide I have also, maybe I'll quickly show you the demo of this one. Let me open the code. Because of lack of time, I have to skip something. Oh, sorry. Sorry, that is bad. Okay. Just a second. So I was using this one. Okay, so let's move to another folder. Yeah, in linear regression, we want to go to LR. Okay. We need to go to inside code. Logistic regression is there. Let's run Jupyter Notebook. Yeah. So in this notebook, I'm going to show you how, given a movie, this is not Twitter, this is a movie reviews. So somebody gave you the movie reviews data and you want to find the sentiment of the people about that movie. All right, that's the problem. So yeah, so this is some initial setup. I have set the directory where the data is. So, and the output file is the processed file. So you can download the dataset from this Cornell website, or if you just search movie review dataset, you will get this data from the Google, right? So if you open and see the dataset, it contains lots of reviews written by people. Film adapted from comic book had plenty of success and so on, right? Whether they are superheroes or not. So people have mentioned this stuff, right, in the data. So you want to analyze this review data and want to predict the sentiment, whether people feel positive about that movie or negative about that movie, or they are neutral. So we want to do that. All right. So here we have some initial setup to load the data. So we have in the directory, once you get the download this data set, it has a directory of two types. One is your positive folder and another is negative folder. The POS folder contains all positive reviews and the negative folder has negative reviews. There are 1,000 reviews in total. So if you just look at one of these review, it looks like this. It's a really long review. Okay. So it's one of the reviews. So we want to analyze this text data. All right. So here, as I mentioned in the beginning of this talk, we want to do some data cleaning. So this code cleans, removes this punctuation, removes the token, remove the stop words and so on, make it lowercase and so on. So you do some cleaning and other stuff. And yeah, that this function will return you the clean data, clean document. So in natural language processing, that's another machine learning thing. So we call a review as a document, okay? And here, if you print after cleaning and other stuff, tokenization. So here the review, the same text which you saw here, after cleaning and tokenization, it looks like this. It splits the review into single words. Okay, there are lots of words actually. Okay. Then we are in step 3, we are building the vocabulary of all the unique word in that review. Okay, so total we got vocabulary size is 46,000. So there are 46,000 unique word. All right. So here we are counting the frequency of each word. So film has been mentioned around 88,000, sorry, 8800, and movie has been mentioned, let's say 5400 and so on. So this code, gives some statistics of your reviews, how many times each word appear and so on. And finally, we save the data. So we process the data, tokenize, filter and so on, and we save the data into some file. So this code saves the data. And here in this part, we modeling starts here. We load some libraries. We have this scikit sklearn feature extraction thing. We are using count vectorizer and tf vectorizer. All right. So in this step, we load the data. Same thing. We are loading the data. Load the dictionary that we already prepared in the previous step. Okay. Dictionary means how many unique words are there in the reviews. And here we are using this TF-IDF approach for encoding the documents or the reviews. So TF-IDF tells you that how many times a particular word appears in a document. So term frequency. So here we are, so TF-IDF you can think of, this is a feature extraction from the text data. It's one approach to extract the features from the text data using this TF-IDF vectorizer function in the scikit library. So you pass this argument, you can take a look at the signature of this function in the library, sklearn library, which is very popular machine learning library. And once we do the TF-IDF thing, we fit the data and we get this X thing. So this raw data, X and Y, gets converted into this vector format. Okay, so this is the data conversion into some numbers, because computer doesn't understand the movie word. Okay, you need to convert each numbers into each word into some numbers. This is done via IDF vectorization thing. After we have this split the data into train and test data. Okay, we do some random shuffling of the data, and then we split the data into, so total we have 2000 review, we split into 1500 and 500, 1500 for training, the rest for testing, and we print the shape of our data. So there are 1500 movie reviews, and the feature vector is 14,000 approximately. And here we have custom logistic regression model. So this is the code written by me, the way you should write a machine learning code, where you have some init logic, some fit function. So this function will give you the sigmoid value, right? 1 divided by 1 plus e to the power minus g, right? So we have coded all those functions. And then there is a loss function, that is our cross entropy loss here. Okay, and then we are fitting the model, that is finding on the running the gradient descent here in this loop. Okay, so here you are computing the gradient, and then taking the next step of gradient descent, and then this function, these two functions will predict the probabilities. All right, and eventually when you call this function, logistic regression function, this one, the class object, and you fit and do the prediction, you get this. You see over time the loss is decreasing, that means model is converging and going towards the minimum, and the accuracy through this code you are getting is around 83%. Okay, And if you're using, instead of writing your own logistic regression code, you can also use the logistic regression function, which is available in this linear model scikit library. So you can directly use those things, so matrices and other stuff. And if you run that library, you get around this accuracy 86%, which is around more than this one. The reason is that these libraries, they are highly optimized. Okay, so instead of directly coding on your own, you should consider using these library functions which are highly optimized, and they run faster because of multi-threading and other stuff, right? So that's how you should use this library. All right, and we have plotted the confusion matrix to see how many true positive, true negatives, false positive and false negatives are there, right? So that's another hands-on how you should try this logistic regression, linear regression. So this was the starting point to your machine learning adventure. So I encourage you to download this code and try to do play around the data and try to fit different models. You can read stuff for scikit library documentation, or read some blogs to get your heads around. All right, so I'll stop here and let me know if you have any question. All right. Okay. No question? Okay, I think, yeah, okay, that's good. You can also email me in case if you have any question regarding this stuff here or anything else. And I thanks again for the audience patiently listening. Okay. Uh, and I also thanks to Dr. Maliga uh, for organizing this one. So, okay. So Dr. Maliga, are you there? Yeah, Dr. Sri. Okay. Okay, so I'll leave the meeting. Hmm? Okay, thank you everyone. It was nice interacting with you all.